Hello everyone. In this week, we have been looking into seismic design of steel buildings. In the last class, we posed a design example problem of a special moment resisting frame in a steel building. In that, we have also mentioned that the beam happens to be the most ductile element, or in other way, we desired the first failure to happen in beams in form of plastic hinges at the beam end. Columns are capacity protected element in that. In today's class, we will start our discussion with seismic design of steel beams along with ductile detailing. So, let us look into seismic design and ductile detailing of steel beams. So, the first thing which we will look into design of beams is about the selection of an appropriate beam section. In this case, for good seismic resistance, we will be selecting only doubly symmetric sections. It may be standard rolled section or it may be built up section. But in case of built up section, we need to have a continuous flange to web weld. We cannot get away with tack weld. Then further, in order to have a stability in our steel building, we need to prevent global and local buckling of beams, so that our beam can have ductile failure in form of yielding. So, in order to prevent global buckling, we should limit our unbraced length to the minimum radius of gyration. So, that ratio is called slenderness ratio. So, let us assume a simply supported steel beam. The top flange of the beam will undergo compression and the compression flange will tend to buckle. Because of the web, the compression flange is unable to buckle in this direction. So, there will be a tendency to buckle in the lateral direction. So, the beam will undergo a bowing action like this in the compression flange. The tension flange will try to restrain this movement. So, we need to restrict the length of the compression flange, or we need to provide sufficient bracing. So, this slenderness ratio, that is the ratio of maximum unbraced length of the compression flange to the minimum radius of gyration of the section Ry, should not be greater than 25. This is true over a distance 2b from the beam column connections. So, it is at the beam end, whereas in the remaining beam, that is apart from the 2 dB at the ends, in the remaining portion we can have the slenderness ratio going all the way up to 0.1 E divided by Ry Fy-B. We have learnt about Ry in this week, where we have mentioned that it is the material uncertainty factor in yield strength, and is the yield strength of the material used for beam, that is steel. So, apart from this global buckling, which is usually manifested in form of lateral torsional buckling in case of beams, beams may also undergo local buckling, in which part of the cross section will tend to buckle or deform its shape. So, in that case, we need to limit the slenderness of various components of the beam section. So, in case of parallel flange I sections, the flange width to thickness ratio needs to be restricted to 9 times of epsilon divided by square root of Ry. Here epsilon is square root of 250 divided by the yield strength of steel used in the beam. Similarly, the web depth to thickness ratio is also restricted to 44.5 epsilon divided by square root of Ry. Ry in both the cases are the material uncertainty factor in yielding for the steel. Now, if you compare these values against table 2 of IS 800, then there is a lot of difference. So, these values are obtained from table 2 of IS 18168. In table 2 of IS 800, where you have the section classification available, you are free to use sections which are compact and semi compact, which have slenderness higher than this. So, what it essentially means, that imposing these limits limits your boundary of using various steel sections. Now, most of the steel sections which will be eligible to be used in beams in seismic regions will essentially be plastic sections. Okay. So, that you can infer if you see both the table 2 of IS 800 and IS 18168 parallelly. I suggest that you keep one copy of the code along with you while going through these lectures. Now, once we have been able to avoid buckling in our steel beam, we will be designing the bracing of the beam. Why? Because only imposing these guidelines about slenderness is not sufficient. We need to provide bracage in order to implement these. For example, here it talks about limiting the unbraced length of the compression flange. So, you need to brace it. So, how will you do that? So, we need to restrain the rotation about longitudinal axis at the supports as well as at intermediate locations using internal panel bracing without any external rigid support. What does this mean? Here I have shown there are 4 beams which are running in parallel, and these are your bracings as shown over here. You have end bracings near the supports, you also have intermediate location bracings as shown in these cases, and these are meant to restrain these beams from undergoing lateral torsional buckling. If you want to know more about lateral torsional buckling, a course on design of steel structures or any textbook for that reference shall be very helpful. Now, at this point we should also understand that these bracings should not be founded on any external rigid support. So, these panel bracings connecting one beam to another is able to restrict the rotation about longitudinal axis for both the beams. So, there is no external support for these bracing. Now, this lateral bracing of the beam should be attached to the compression flange, but in case there is an inflection point where your bending moment changes sign or your curvature reverses, in that case there is a chance that the compression flange will become tension flange and the tension flange will become compression flange. So, in that case you need to attach this lateral bracing at both the flanges. Okay. Then we need to find out the shear stiffness of this panel bracing which is closest to the inflection point. For such cases, your shear stiffness of the panel bracing should be at least equal to 10 times of Ry times of MPV divided by length of bracing into dF. All these symbols will be more clear when we look into the illustrative example in the next class. Then the shear stiffness of panel other than the vicinity of inflection point is little relaxed. You can have half the stiffness of the panel which is closest to the inflection point. At the same time, the shear strength of the panel bracing system shall be 0.025 Ry times of MPV divided by dF. This shall be the minimum value of the shear strength of the panel bracing system. We will illustrate these through an example problem in the upcoming class. Then at any plastic hinge location which is usually at the ends of the beam in case of simply supported beam, in case of cantilever it is close to the fixed end. Then in such cases both flanges are to be laterally braced and the axial strength of the bracing shall be given by this very expression, and the shear stiffness is the same as the shear stiffness of the panel as shown over here. So, we will see this how we will satisfy the ductile detailing related to bracing of beams. Try to understand that this bracing is different from the braced frame which we were discussing it earlier. The frame may be unbraced, the frame may be moment resting frame, and still these beams may be braced. So, for clarity these bracings shall be called as panel bracing and the bracage used in structural system will be termed as structural bracage. Okay. Once we have satisfied these checks related to preventing global and local buckling of beams, then it is time to design the beam for flexure and shear. In order to obtain the flexural strength of the beam, we need to arrive at the result using load combinations which are specified in IS 1893 part 5 and IS 18168 2023 for capacity protected elements. These load combinations have been dealt in detail in lecture 7.1, the first lecture of this week. Then we need to assess the design shear strength of the beam, whether the shear strength of the beam is higher than the shear demand or not. So, in order to estimate the shear demand, we need to consider capacity design principle, considering beam bending in double curvature, plastic hinge of strength 1.1 times of Ry times of Fy times of ZPV, assumed to act at a distance of dB by 2 from connection end, and the gravity load required to be carried. So, all of these are available in clause 6.4 of IS 18168. You can have a look in parallel to these lectures, and based on this we shall be able to find out what is the shear demand. In most of the cases you will find that a linear structure analysis will give you the shear demand. Then for obtaining the shear capacity, we need to consider plastic shear resistance first, which is given by the shear area multiplied with the yield strength of the web divided by root 3 gamma m0. Now, why are we considering the shear area or the area of the web or the yield strength of the web of the beam? Because in an I section the flanges are meant to carry bending and the web is meant to carry shear. So, that is why we are considering shear area of the beam, that is the web area, and Fyw is the yield strength of the web of the beam. Now, typically for rolled section you will have the similar Fy for the entire section, but in case of built up section you can have different Fy for web and flange, but in most cases you will have the same value of Fy for the web as well as flange. Now, in this case the partial safety factor against shear failure is taken as 1.1, and there is a factor of root 3 which comes from the shear failure criteria. And then we will also check the strength of the web in shear buckling. Webs are prone to shear buckling. When are they prone to shear buckling? When the depth of the web is excessively high compared to its thickness. We will come to that. When do we need to check the web in shear buckling? Here we have two different methods: simple post critical method and tension field method. Any of the methods can be used depending on your preference and convenience. Then however the basis of both the methods are very different. Now, after designing the beam for flexure and shear, we may need to provide splicing in beams, because your structural section may not be that long, or you may have to change the dimension of the section. Then in that case we will provide the splicing. The splice location should be at least 3 times of depth of the beam away from the column face, or at least depth of the beam away dB away from the concentrated force. In most cases in buildings you will not have very high concentrated force, except for industrial structures where you may have some machinery installed and you will have some concentrated force. Then the design strength of a splice should be at least 80% above the required beam strength. And when you will have a splice, in most of the cases how will you make the splice? You will have a plate attached to the flange on either side of the beam, and for the bottom flange as well, and the webs will be also connected through web splice plate. For the flange splice plate, the design strength should be at least 1.2 times of Ry times of Fy times of Af, which means it should be at least 20% more than the maximum possible strength of the flange. Now, why am I telling it maximum possible? Because Fy times of Af gives you the yielding strength of the flange, and if you multiply it with the material uncertainty factor in yielding, you get the maximum possible strength, and then you also multiply it with 1.2, that is 20% plus. It will be more clear when we illustrate it through a design example. So, let us summarize what did we learn in today's class using the design steps, or let us provide a systematic method how do you design a steel beam for good seismic resistance. So, the first thing is to obtain design forces and bending moments. So, design bending moment and design shear force. Then we will arrive at a suitable section. How we will arrive? We will determine the required plastic section modulus. So, based on this plastic section modulus requirement, which is calculated as mu divided by Fy by gamma m0, mu is the design bending moment, Fy is the yield strength, and gamma m0 is equal to 1.1, which is the partial safety factor in yielding. Then in this case we get the required plastic section modulus ZpZ required, and based on this value we shall assume or we shall choose a section from a steel table. Now, after choosing a section, we will note down different geometrical properties of the section from the steel table. Based on various geometrical properties such as width and thickness of flanges and webs, we shall classify the section into plastic, compact, semi-compact and slender. This is based on table 2 of IS 800-2007. Now, you might be wondering what are these different classes of sections. So, and many of you may be already aware with these classes of steel sections. So, the plastic section is able to attain plastic moment, and then it has sufficient deformability or ductility so that it can have a very ductile failure mode. When it comes to compact section, it is able to reach the plastic moment, but it is not able to have sufficient deformability. Semi-compact sections on the other hand are able to reach the yield moment, but they are not able to reach the plastic moment. At the same time, slender sections do not even reach the yield strength or the yield moment. Why do they not reach yield moment? Because before yielding they undergo failure through buckling. Okay. So, after classifying these sections, we shall also check for ductile detailing of the section. So, we will calculate the slenderness ratio of the section, which is the ratio of the maximum unbraced length of the compression flange to the minimum radius of gyration of the section, and we shall compare that using prescribed limits. Then we shall also compare flange width to thickness ratio and web depth to thickness ratio using these limits, which are specified in table 2 of IS 18168. Now, at this point I would like to reiterate that most of the sections which will pass these ductile detailing tests will be your plastic section. Now, once we have the section properties and classification known to us, we can find out the design bending strength. The design bending strength of beam is calculated in two different manners for laterally supported beam and laterally unsupported beam. As we have seen, in most of the cases for good seismic resistance, you need to support the beam by providing panel bracing, internal panel bracing. We will discuss more about that further, but sometimes the beams may be considered to be laterally unsupported. Okay, so for laterally supported beam, the design bending strength is given by MD equal to beta B ZP Fy divided by gamma m0, where gamma m0 is equal to 1.1. ZP is the plastic section modulus and Fy is the yield strength, beta b is equal to 1 for plastic and compact section and equal to Jd by Zp for semi compact section. Now why do we choose beta b to be equal to 1 for plastic and compact section? Because these sections are able to attain plastic moment carrying capacity. On the other hand, semi compact sections are able to achieve yield moment and they are not able to attain plastic moment. Therefore, by choosing beta b equals Jd by Zp, we are essentially saying that it will be equal to Jd times of Fy divided by gamma n0, and then we will compare the design bending strength Md against the design bending moment, that is the demand Mu, which shall be given in the example problem, or you shall obtain it using linear structural analysis on any of the commercial software. Now let us look into the estimation of design bending strength for a laterally unsupported beam. A laterally unsupported beam is prone to undergo lateral torsional buckling. So the design bending strength in this case will be reduced. It will not depend on Fy, rather it will depend on Fbd, which is the design bending compressive stress considering the potential of buckling. Zp and Zd are plastic and elastic section moduli, and beta b we have already seen. You can obtain the value of Fbd directly from tables 13a and 13b of IS 800 2007, or they can be calculated using the expressions shown over here. These expressions are also adapted from section 8 of IS 800 2007. Here you can see that Fbd equals chi LT times of Fy divided by gamma n0, where you have the value of chi LT given like this, and then you have the value of phi and lambda, and finally you have the value of alpha LT, which depends on what kind of section is this. Okay, so whether it is a rolled section or it is a welded section, and then all these depend on MCR or FCRB, which are provided in table 14 of IS 800 2007. I hope most of you are already familiar with this design step of a laterally unsupported beam. After finding the design bending strength, we shall compare the design bending strength against the design bending moment Mu. After designing the beam for flexure, it is time to design the beam for shear. In case of shear, we will first evaluate the plastic shear resistance of the section. We will calculate it at Vp equals Av times of Fyw divided by root 3 gamma m0. We have already seen this expression earlier in this class, and then for sometimes when d by Tw, which is the ratio of depth of beam to thickness of web, is greater than 67 epsilon for web without stiffener and 67 epsilon times of square root of kV by 5.35 for web with stiffener, then you need to check the strength of the web in shear buckling, because this kind of slender web actually is prone to shear buckling. For this you will implement two different methods, simple post critical method or tension field method. If you look into the simple post critical method, VCR is the strength of web in shear buckling, is given by AV times of tau v, and AV is the shear area of the beam and tau b is the shear stress corresponding to web buckling, which is given by these equations, which finally depend on non-dimensional web slenderness ratio for shear buckling stress. This again depends on elastic critical shear stress of web and some other factors which are provided in the code IS 800. You can always have a look into this. It will be more clear if you implement this using an example problem or a real life design. When you are using tension field method, then you have the expression of a strength of web and shear buckling as VTF being equal to AV tau b plus 0.9 times of WTF into TW into FV into sin phi, and this has to be less than equal to Vp. What is Vp? Vp is the plastic shear resistance in shear. Vp is the plastic shear resistance. Then after finding the strength of web in shear buckling using either simple post critical method as VCR or using tension field method as VTF, we shall find out whether it is lesser than Vp or higher than Vp. The lesser of the two, that is minimum of Vp and VCR, or if you have implemented tension field method, then the minimum of Vp and VTF shall be considered to be the design shear strength, which has to be compared to the design shear force. After completing this design for shear, we shall find out whether the shear is high or low. If your factored or the design shear force is less than or equal to 60% of the design shear strength or the capacity, so the demand is less than equal to 60% of the capacity, then we will define it as low shear case, and in this case we do not need to reduce any design bending strength. So what we have determined MD stays the same, but if your design or factored shear force is more than 60% of the shear demand, if your factored shear force or the demand is more than 60% of your shear capacity or the design shear strength, then we define it to be the high shear case and we need to reduce the design bending strength. It means that for such a high shear, the design bending strength cannot be leveraged and you need to reduce your design bending strength. The reduced design bending strength is given by MdV, which is equal to MD minus beta times of MD minus MFD, and this has to be less than equal to 1.2 times of ZD divided by gamma m0, and this is true for plastic section. For semi compact section we do not do any reduction because the section is anyway reaching only the yield moment, it is not reaching the plastic moment. So we do not need to reduce any design bending strength in case of semi compact section. But as we mentioned earlier, in most of the cases due to ductile detailing you will be only be able to use plastic sections. So ultimately you will be left with this process. Okay, where beta is given by this expression as shown over here, and MFD is the plastic design strength of cross sectional area excluding shear area. So we shall be only considering the flanges of an I section and considering partial safety factor gamma m0. It will be more clear as we look into the illustrative example. After arriving at the structural adequacy of the member, it is also important that we design the lateral bracing in the beam. We need to design the panel bracing. So we have seen all these ductile detailing guidelines. We shall try to satisfy these by providing the lateral bracing in the beam, which are internal panel bracing, and then we shall also try to satisfy the splicing criteria given in IS 18168 for ductile detailing about the splicing location, about the design strength of the splice, about the design strength of flange splice plate, etc. So in this class we have looked into seismic design and ductile detailing of steel beams. We have looked into codal guidelines. We have also established the design steps which we shall perform in order to obtain the seismic design of steel beams. In the next class we will illustrate the same using an example problem. Thank you.